Hello, my name is Roy Simpson, and I'm a professor of mathematics at Cosine College in Sacramento, California. This is another proof in my Proofs in Differential Calculus series, and this is kind of the mother of the trigonometric derivative proofs. So this will be the derivative of the sine is equal to the cosine, and you could use this as kind of a basis to help you prove pretty much any of the other identities, any of the other trigonometric derivatives. Well, technically, all you really need to do with this one, what this one will help you with, is derivative of the cosine. The rest of them actually fall out from the product and quotient rules, pretty much the quotient rule, actually. So your instructor might ask you to possibly take the derivative or show that the derivative of the cosine is the negative sign. That's generally how it's done. They should show you this proof in class, but perhaps maybe you didn't get it in class, so you might need some help with it here. Let's go ahead and look at some required prerequisite knowledge. I'll go ahead and go to the next page to get that. There we go. Prerequisite knowledge is the thing that you should know. You should definitely be very familiar with the limit definition of a derivative by this point. You should also be very, very familiar with trigonometry. That's an incredibly important piece of information. That whole entire course is a huge prerequisite for calculus. You should also know that the limit as theta approaches 0 of sine of theta over theta is 1. And you should also know that the limit as theta approaches 0 of the cosine of theta minus 1 over theta is 0. Those last two are proven in my playlist. So if you look at the differential calculus playlist, they are back to back, right next to each other. Now this proof, I'll go ahead and do it on this screen here. I'll just do kind of like what I did with my last proof, if you are kind of following through the chain of proofs here. And we'll take the actual definition of the derivative to do this. So the derivative with respect to x of the sine of x is actually just going to be the limit as h approaches 0 of the sine of x plus h minus the sine of x all over h. That's one of the definitions for the derivative. Now, as I look at that, it looks to me like it's going to be 0 over 0. So that means I'll have to probably start a trick. Now, when students are left alone to their own devices, I've seen a lot of things happen here. They multiply top and bottom by the conjugate of the numerator, which is a great tactic, but there's actually an easier way to approach this. So I'm actually going to do the easier way to approach this part. So this will just turn into the limit as h approaches 0, and from your trigonometry prerequisite, you do know that the sine of x plus h can actually be rewritten as sine of x times cos of h plus sine of h times the cosine of x. And of course, from that we still have minus sine of x, and this is all over still h. Now that identity in blue right there you should know from trigonometry. What I'm going to do is I'm going to go ahead and rearrange that numerator so that I get stuff with sine x's next to each other. This is kind of, through trial and error that you find that this is the way the proof should be done. So I'm just rewriting the sine of x times the cosine of h here minus the sine of x, so I get them next to each other. And actually, not only that, I'm actually going to break this, not the limit, but break the fraction. So I will also have plus and then another fraction to be sine of h cosine of x all over h. Now remember, this is all inside this limit. Now if you take a look at that first term, I can factor a sine of x out, and actually I'm going to go ahead and try to break this limit. So that means that I'm going to just break the limit and hope that what I break it into, the pieces that I break it into, actually exist. Now right now it might not be obvious that these limits actually exist, but what I'm going to go ahead and do is just state that since sine of x does not rely upon h, I can actually pull that out in front of that first limit. And since cosine of x does not have an h in it, I can pull that out in front of that limit. So when I do that, I get a beautiful sine of x and then times that limit. And then the second term, like I said, I'm pulling out the cosine of x. And again, that's times that remaining limit. Now, both of those limits should look very familiar because those were my required prerequisite knowledge. Limit as my variable goes to 0 of sine of the variable over the variable is equal to 1. So this limit in the back, and I'll go ahead and highlight that here, this limit where the variable is approaching 0 of the sine of the variable over the variable itself, that will approach 1. Also, if we look at the other law here, or the other limit, sorry, the limit is the variable approaches 0 of the cosine of the variable minus 1 over the variable. That is going to turn into 0. So that actually looks dead on like this guy right here. So that first limit will turn into 0. That second limit will turn into 1. You can already kind of see the writing on the wall that if that first limit turns into 0, we've got 0 there, plus that second limit turns into 1, we get the cosine of x by itself. So this all equals the cosine of x. And that actually proves that the derivative of the sine of x is equal to the cosine of x. Now, one last thing I want to mention here is that we split the limit from here to here. I want you to be very aware that I was trying my best the entire time. So when I split the limit, I was trying my best to make sure that after I split the limit, that both these highlighted limits turned into something finite. If one of them turned into infinity or negative infinity or just didn't exist at all, then I would have to rewind back to this step right here and have to somehow work with the limits. No, I wouldn't be able to split them. Very, very important to mention that because if you start splitting limits and without checking to make sure that those splits are finite, you're going to get in a lot of trouble. All right, we are done with this proof. QED.